Bismillah ar-Rahman ar-Rahim. Here's an example of a 3 by 3 matrix for finding the eigenvalues and eigenvectors. We consider the tridiagonal matrix A with 1s on the main diagonal and -1 on the subdiagonals. It is a symmetric matrix, so we expect that the eigenvectors will be perpendicular, mutually perpendicular. Okay, so to calculate the eigenvalues, we take the determinant of A minus lambda I. If we expand the determinant, we get the characteristic polynomial. Starts with lambda to the n, which is lambda cube, okay, which factors into quadratic factor and lambda minus 1. So we have lambda 1 equals 1, the first eigenvalue, and then the quadratic factor gives two eigenvalues, lambda 2, 1 plus root 2, lambda 3, 1 minus root 2. Okay. Now, the eigenvectors will be a basis for R3 as well as the column vectors of A, and they can be grouped into an orthogonal matrix if we make every vector a unit vector. So to calculate the eigenvectors, we start with lambda 1 equals 1. So 1 minus 1 gives 0 on the main diagonal, and here if we subtract row 1 from row 3, we get a row of zeros. So x1 is x, y, and z. So the z is a free variable. We take it to be 1. Then from the first row, y will be 0. And if we take the second row, we will get x equal to minus 1. So the first eigenvector is minus 1, 0, 1. And you can check that the product of A times x1 is equal to x1. Then for lambda 2, we calculate the eigenvector. Again here, if we eliminate below the first pivot and then below the second pivot, we get a row of zeros. So third component of x2 is z is a free variable, so take z equals 1. Then we'll find that y is minus root 2 and x is equal to 1. So this is the second eigenvector, 1 minus root 2, 1. And you can check that x1 transpose x2 equals 0. Are perpendicular to each other. Similarly, for lambda 3 equal to 1 minus root 2, we calculate the eigenvector x3. Okay. Following the same procedure, we get a 0 row. Okay. And hence we get the eigenvector x3 is 1 root 2, 1. Again, x2 transpose x3 equals 0. We get 2 minus 2 equals 0. And also x3 transpose x1 will be 0. Now, if we calculate the length of each eigenvector, the norm of x1 is root 2. The norm of x2 and the norm of x3 are equal and both equal to 2. So we divide by the lengths. We get the matrix Q. This is the matrix of eigenvectors, which is an orthogonal matrix. Each column is orthogonal to the other columns. We will denote the eigenvector matrix by capital S. Okay. Some important remarks here. If you take the product of the n eigenvalues, you will see that they are equal to the determinant of A. And if you take the sum of the n eigenvalues, they will equal the sum of the diagonal entries of the original matrix A. This number is called the trace of A. So the trace of A is the sum of the diagonal elements, A11 plus A22 up to ANN. And this is equal to the sum of the eigenvalues. These two rules provide us with a good check on the calculation of the eigenvalues and the I. So if the calculation is correct, product of the eigenvalues is equal to the determinant and the sum is equal to the trace. Now, I have to caution you, if you add a row of A to another row or exchange rows in A, the eigenvalues usually change. As a conclusion, the procedure of Gaussian elimination does not reserve the lambdas. After elimination, the triangular U has its eigenvalues along the diagonal. They are the pivots, but they are not the eigenvalues of A. So be careful. If we take an antisymmetric matrix or a skew-symmetric matrix, like the rotation matrix for 90-degree rotations, it is 0, 1, minus 1, 0. This matrix has no real eigenvectors or eigenvalues. Okay, so if we calculate the characteristic determinant or characteristic polynomial here, we get lambda squared plus 1 equals 0. So lambda is either plus or minus root minus 1, which is I. It is pure imaginary. So lambda 1 is plus I, lambda 2 is minus I. Then we can calculate the eigenvectors from A minus lambda I or Q minus lambda I minus lambda I is, we get the first eigenvector. Okay, so it is x1 1I, and if we calculate the second eigenvector for lambda 2, so minus I, we get x2 to be 1 minus I. Now, this matrix is not symmetric, it is skew-symmetric. And here also the eigenvectors are orthogonal, but orthogonality here is orthogonality for complex vectors. And the rule, which we will take up in chapter 10, is x1 transpose conjugate. We take the conjugate of x1 transpose and multiply by x2. So it is 1 minus I times 1 minus I, and it will be 1 plus I squared, which is minus 1. So 1 minus 1 equals 0. So they are orthogonal, but now for complex eigenvectors. So important remarks here is that Q is Q-symmetric, which means Q is minus Q transpose. Each lambda is pure imaginary. Q is an orthogonal matrix, so the absolute value of each lambda is 1. So a symmetric matrix has A equals A transpose, we have real lambdas, and the skew-symmetric matrix, A transpose is minus A, we have purely imaginary lambdas.